Hold on. I think needs to be. Yeah, you can begin.
Okay. Hello, everyone. Welcome to our presentation. Our team is formed by Uribe, Bernat, Jorge, and I, Claudio, and our advisor is Issey. The topic of our project is an image-to-image translation problem using the XGAN architecture. This architecture was proposed in a paper from 2018, authored by researchers at Google Brain, and it solves the task of mapping images from one visual domain to another different domain. There are already some other architectures that solve this task, but this one has a few major strengths or advantages. I'm going to name the more important ones. First, that it learns a semantic representation rather than making a pixel-to-pixel translation. That it doesn't, so given an input image, there is no mapping between two datasets of what would be the other image. And the other strength or advantage is that it's unsupervised. So it could be supervised if, for example, for each dataset, for each image, there was annotations, but that would be a very costly task, especially for the dataset of real images. So the paper proposed this example of converting cartoon images to real faces and vice versa. And in our project, we followed the same example. However, it can be used for many other applications. For example, for converting landscape pictures into paintings of the same landscape, transforming sketches into images, or even from one domain, which is text, to convert it to image, which is a completely different domain. So why did we choose this topic as our final project? Because it's a very powerful architecture with a wide range of applications. Because we like generative adversarial networks. We are not original on that, but we would like to be able to develop them professionally. And why not? Because it's cool, the results that we can obtain with it. Everyone could appreciate this example of cartoon to real faces to cartoon. I'm actually going to show how the evolution of the training was. So we thought that we would be very satisfied with the results. We would take a look on the architecture and on the training process later. So I'm going to switch to the milestones. We defined six main milestones. We achieved more or less all of them, and the same milestones, but in a time fashion way. So the overall objective was to achieve image-to-image translation. We decided to face the challenge with a simple initial step, which was implementing a single domain GAN. Just be able to generate cartoon faces from random noise. And for doing that, we had to first get familiar understanding GANs. And later we added the implementation of the autoencoder to using between multiple domains which is the actual XGAN. Later, we improved the losses. We improved the quality of the results by adding complementary losses, and finally, we also compared with other alternatives, other implementation of XGANs made by other teams around the world, and also non-XGAN alternatives. Okay, so how did we implement how did we code the model? We used Google Colab at the beginning because it is a great tool for sharing, well, to make the code self-explanatory, and later, since we had to deploy the code to Google Cloud and also to GitHub, we switched it to plain Python. The model was implemented using the TensorFlow API with Keras, and we took the opportunity of the Google Cloud coupon codes to create a virtual machine and make more extensive trainings there.
All right, so I'm going to talk now about the datasets. Just 1 second. There we go. So I'm actually remarking datasets because as we want to do an image-to-image mapping, and those images are obviously different because we don't want to go from one dataset to another. We actually are using 2 different datasets. So let me explain both of them. Actually, as commented, we are working on the same semantic context, which are faces itself. And we need 2 datasets. One, the cartoon, which will be the resulting set, and the other one, the human faces set, which will be the one that we will give as an input. Obviously, XGAN is supposed to go from one domain to another, so it won't mind if we want to go from input to output. But we will later explain why we only wanted to do one test, because we ran out of time. So it's quite important to remember. But still, XGAN is an architecture that supports this cross-domain with regarding the order. So let me explain a bit the cartoon dataset. It was actually the main starting point from this project, as it was like what we first saw and where the idea came from. This cartoon was developed by Google, and it was used for the project to develop the XGAN architecture itself. And it was proposed, it actually gives us 100,000 images, all of them annotated with 16 different attributes for each face, and this is pretty good. As we are doing unsupervised learning, we are not using these annotations, and we are just using the image itself. We also have a small data set that is given by Google. It's 10,000 images, and we also use that for some testing purposes or for just small training parts of our implementation. I just want to say that this dataset was quite clean. Images were super clean. Backgrounds were cleaned also. Faces were cropped. It had a huge blank space, but images were centered and everything, so it was really good to work with that dataset. The only thing is that we noticed that if we actually crop each face into a smaller portion, the training was super fast because we're actually giving less inputs, as we could just avoid giving too many blank pixels that were nonsense for the training. We were also avoiding some problems because sometimes our network was trying to deduce if on one corner it needed to have something like hair or something like that, which in theory it would not, because all of the images had a blank space margin. So yeah, quite simple, but still important to understand that having this blank space cropping was super useful for our project, and it was like a good starting point to see that pre-processing data, even of small bits, was super useful for that. So let me go and talk for the next data set, the faces one. Actually, the XGAN paper proposes to use the BGG face dataset. But we didn't actually found the data set cleaned, and that's supposed a problem because we had a data set similar to the one that you're seeing in this slide, but the problem is that it was not cropped, it was not centered, and it didn't have a clean background. And this supposes a problem because we had a super clean data set, which was the cartoon one, but then we had like a noisy one from faces. And we tried to see solutions for that. We tried to search in the internet for a data set that was clean as the other one, but we didn't find any. So we actually tried to go with the Celeb A data set and tried to clean it by ourselves. The good thing about this dataset is that it was centered and cropped. As you can see, we made this a small GIF that you can see that the mouth, the nose, and the eyes are always in the same position, just like the other dataset. And this is good because we are working on the same semantic problem and context. And this was good because the semantic laws could use this for its machine learning things. So yeah. The problem was that the background was not clean. So we actually did a small Python script and used an API from our website and tried to clean it ourselves. The problem is that this is quite computing expensive, and we actually just cleaned 1,000 images. But still, it worked in order to start with the project and understand like all the bits and pieces of this information. So yeah, this is about the data sets, and now I'm going to talk about the first experiment that we did. We actually started with a single domain gain. It was like just taking the lab session because we actually knew how to do an MNIST, but okay, how do we generate faces from a face? So what we did at the beginning was to just understand TensorFlow and a bit more about GANs, and we took the data set of cartoon faces and changed it for the MNIST and did some different adjustments. In this case, a set, we just took the same architecture, added some extra COM layers, and just used the RGB channels because we were actually only using one on the lab as it was black and white images. So yeah, we did these small changes. We used the same optimizers and losses, like the binary cross entropy and the atom. We actually had the same, I don't recall, but I think it was the same noise vector. And yeah, it really worked well. So well, after a bunch of iterations, obviously, but we did also some learning rate values changing. We also saw that normalization of data from -1 to 1 was super helpful if you had a TAN-H layer at the end. So yeah, after a bunch of iterations and a bit of research on the internet and some tips and tricks that you could see on other Medium posts probably, we actually finished with some interesting results. And after a bit of training, we could finally see some faces, which was good. And yeah, you can see here the different losses from TensorBoard and what epoch 0 looked like and what epoch 100 looked like. And you can see that there are some cartoon faces. So yeah, first experiment successful, and this served as a starting point from the XGAN that Roger is going to talk about.
Yes, thank you, Bernat, and hello, everyone. So yeah, the idea was that all the learning we had about performing GANs in a single domain, take it from there and develop the multiple domain XGAN. And as we will see now, there's like a lot of parts on the model which are the same. So it was like a really useful step to fully understand and then go through implementing the XGAN based on the paper. So the XGAN is basically an extension of the GAN. As Bernat was saying, the GAN has a generator and the discriminator. But for the MNIST and also for the cartoon set, what we have is that from a random noise, we get to the cartoon image. And then the discriminators, it's trying to say if it comes from the data set or is it really generated by the generator. But in this case, what we will have as a generator is an autoencoder, as we will see. The discriminator is going to be the same as the GANs. And finally, there's a binary classifier that is used for improving the training, as we will see now. So what we did to develop the XGAN, we started doing by the generator, and the first part of the autoencoder was the encoder. So as we'll see, we go from an image to an embedding, which is a size of 1024. And for doing that, there's a part of this which are shared layers, and some others not, are independent of each domain. So the encoder has 2 entry points. And when we add the decoder, it's kind of look the same, but transpose. So when you input an image from one domain, you get the embedding, and you get the two images outside from the decoder. And the same for the other domain. As Bernat was saying, the idea of this paper is to do a cross-domain, so you can map from one domain to the other one and vice versa. But for time, we just train it to map from real face images to cartoons, because we started doing in multiple domains and was trying very slow, and we couldn't get pretty good results. So this is the generator, as said. Then we will add the discriminator, which is the same as GANs, just to decide from where the image comes from. And finally, a binary classifier attached to the embedding, which is going to be trained to decide if the embedding comes from one domain or the other one. But how this is the network structure, but how the semantic that Claudio was saying, the self-supervision semantic is learned. So the generator losses are those three. The first one is called the encoder-decoder loss, which simply means if I'm having a cartoon image, the image I will have from the decoder has to be the same and equal for the other domain. And the other two are the ones that make the semantic self-supervision and learn the semantics. So the semantic consistency loss, what it's telling is that I'm going to have a real face image. I'm going to get the embedding, but if I get the image on the other domain, if I put it back to the encoder, I should get the same embedding. And what is trying on the other side, the domain adversarial loss, what is doing is trying to know from where the embedding comes from. So it's kind of doing the opposite things, but what the paper is telling is that this helps really the semantic consistency to learn more. It's kind of what we have with generator and discriminator, that the discriminator is trying to, the purpose of the discriminator is to get the better generator. So moving to the discriminator laws, I'm not gonna explain a lot, but it's because it's the same we had with GANs. And here are some of the best results we got. So we saw that the first epochs, what the generator was learning was to get cartoon images, and later on was learning the semantic itself. So we see like at epoch 200 or 600 that some semantic is learned. So the color of the hair, the color of the skin is kind of consistent in real and in cartoon. But what we got from here is that maybe the cartoon dataset is too much ideal, because the real face images, even though they don't have background, some faces are looking at the right, at the left, or some of them have clothes with color, and this is kind of confusing the network. And if we take a look at the losses for those examples, we can see a bit what we said. The semantic loss, it's starting to decrease after considerably after epoch 100. So what we mentioned, and the discriminator and the generator loss are kind of the training again. It's a bit tricky, and we can see how the losses go and
So good night, everyone. So our last milestone, as Claudio said, we said that we wanted to compare our results, especially visually results, with other alternatives in the literature. So while we were doing our XGAN implementation, like the main one, we also did some research, and we found that the state of the art in this kind of image-to-image translation could be this StarGAN V2, which was presented last year in CVPR. And so we tried to compare this with the already pre-trained model that they have. We have open code, so we have in TensorFlow and also in PyTorch. So we use these codes with the pre-trained parameters to see what happens if you include cartoon faces instead of the human faces that they use to train the models. It's slightly different than the XGAN. Okay, the objective is the same, like image-to-image translation between two different domains, but it's like more direct approach because they have like one encoder decoder. They don't have this X structure that Roger just explained. So what you have to do here is that you input some source images here, and you also have some reference images. So for this StarGAN to do the same that our XGAN and to compare, we have to use cartoons of reference here. And what we found is this could also help us to improve our XGAN model as well, because we were learning some stuff new. So what we get here is that indeed, when you use these human sources and the reference cartoons, you get like the network, which is we think is amazing because it was trained only with human faces. It managed to translate some of the semantic content of the cartoons to the human faces. For example, the skin color, the hair color, and also the hairstyle, whether it is short or long or something like this. We also find some interesting patterns here that also help us then to think about our XGAN and our data set. But because, for example, when you input to this StarGAN model a very unlikely image, a cartoon, for example, a cartoon with a dark skin and a white hair, what you get is the network was not really able to translate these attributes, like this combination of dark skin and white hair. It was like it was unable to do that also in this case. So we realized that it has to do with this celebrity data set that they were using. They were using the HQ version, and we were using as well one of these versions that it could be like bias, and this with different participation of different kind of skin and color of the hair. So we realized this here, and we thought about some ways in which we could improve this, or to make the network to learn even to learn these unlikely attributes like dark skin and white hair at the same time. Then we also did some other experiments, like in the other direction that we couldn't do with our exam because of the time constraints. And what we got here is that if you input like a source image, the cartoon, and you have the reference images, the human faces, you got the opposite, like a cartoonized, a humanized version of a cartoon, which was pretty cool as well. And we also performed some like experiments with this. And our main intention with this comparison was to look how to improve our own XGAN, for example, because with a different structure that didn't imply these semantic consistency laws. So just to conclude our presentation, we have like three main thoughts. First, we wanted to emphasize the importance of data preprocessing, because it's not like really fancy, but for us it was one of the most important things that we could achieve before getting really good results. Only it was after we constructed our own data set for human faces with this background removed that we could manage to get some kind of decent results. Before that, it was not like a matter of an architecture or the model itself. It was about the data. So we wanted to emphasize this about the data preprocessing. We also wanted to say that this strategy of learning to generate cartoon faces in a single domain, and then moving to the generation of the multiple domain cartoon faces, the multiple domain GANs, was really good for us, because they really share like the same structure. At the end of the day, they are GANs, both of them. So we learn how to train them, the same kind of experiments about the learning rate that what we did with the single domain GANs, we also did with the XGANs. And finally, we also wanted to, like, a final thought would be like cartoon faces for us are like useful devices to understand what is going on inside of these image-to-image translation models, because cartoon faces are like simplified humans. So they allow us to focus on a specific attribute like hair color, the color of the skin, and the style of the hair. And then with this, we can see how the model is learning in the inside, even in a different task that didn't involve cartoon faces, but only human faces. We think it's like a good strategy for learning. And that's all. Thank you very much. And any question, we will be pleased to answer you.